So let's go ahead and get started here. This is the first talk of this season's colloquia series, and Gab again is leading this up and bringing in some excellent speakers, just like last year. Our first speaker is going to be Ed Seidel, our current director. It turns out our second speaker is going to be Larry Smarr, our first director. So we have this next couple of weeks will be interesting in that respect. This is one of those situations where it's like, this is a speaker that needs no introduction to this crowd, right? I mean, I don't know that I've ever had it so true before, but I'm going to say something anyway. I think everybody knows that. Everybody knows Ed. They know he's the director of NCSA. They know that Ed comes here by way of Russia, where he was the senior vice president for research and innovation at the Skolkovo Institute. Before that, he was the head of the Office of Cyber Infrastructure and the AD of the MPS, the Math and Physical Sciences Division at NSF, the biggest division that NSF has. Before that, he also led an HPC center at LSU, and we worked with Ed when he was there. In fact, Ed was part of our Blue Waters proposal team, from that position at LSU. What most people know, but maybe not everybody knows, is that Ed really is a distinguished researcher in his own right. He's not just a manager and just a leader and just a director of leading big organizational efforts, but he's very well known for his research in relativity and astrophysics. And before he was at LSU, he spent time leading a group in relativity at Max Planck Institute in Germany, and before that was here at NCSA and University of Illinois doing research here, and got lots of acclaim. And I'm sitting here looking at some of the awards that he's got. It's the 2006 Sidney Fernbach Award, which is just a huge honor. 2001 Gordon Bell Prize, another huge honor. I mean, Ed's very well distinguished in his own right as a researcher. And not a lot of people know that. But one thing that I think not many people know, and that Ed's about to be able to add a whole new line onto his CV, is that tomorrow at 3:30 in the Krannert Center at the Elnora Music Festival, Guitar Festival, Ed's going to be playing guitar with President Tim Killeen.
Now you've got my stomach in butterflies.
So everybody needs to show up. Ed needs to get his guitar out. The last trip he took to D.C., he actually said he took his practice guitar with him. He's walking around the Smithsonian Institute with his guitar in hand. So anyway, that's another side of Ed. If you want to see that side of Ed, then make sure and show up.
Don't do it.
and clap loudly. Then make him feel good, tomorrow. So with that, and without a guitar in hand, I'll let Ed Seidel as your first colloquial speaker.
Thanks, Jamie. I was fine until the guitar part, and then it's just like, so it's just the weirdest thing, I can give a talk in front of a lot of people about things like physics or computing or something, but if I'm holding a guitar, I just fall to pieces. There's just one other person in the room, so that's going to be me tomorrow. But today I'm going to tell you about something that I actually became quite passionate about. Actually, starting way back when I was at Max Planck, or probably really first here, when I saw that a lot of work that's going on in the most fundamental areas of science, mathematics, art and humanities, and particularly when they converge, all kinds of new things come out. It comes back and it really impacts society in a very profound way. And so, as you all know, everyone here knows the story of Mosaic. It's even in my talk here a little bit about how Mosaic, actually, you could trace it all the way back to Albert Einstein, even though you might not make that connection immediately. I did this? It felt like it went off. Okay, good. You might not make that connection immediately, but it's really there. So when I was at the NSF, in the last year that I was there, the director asked all of the directorate heads, and there's 6 of us, to give talks to the entire NSF about their directorate. And so my directorate was Math and Physical Sciences, and I wanted to talk about how important basic research is in the 5 areas of the math and physical sciences. And for me at NSF, if you know the NSF classification, within MPS, math and physical sciences, we have physics, mathematics, astronomy, chemistry, and materials science. So this talk is really oriented towards telling the story of how basic investments in science lead to innovations that really pay back huge dividends in society. And so the reason I thought it would be fun to give this talk here is that, first of all, I think it's a story that needs to be told more and more often, but I think this university is a little bit of an unsung hero, I think, at the national and international level in terms of all of the amazing things that have come out of this university that have come back and impacted society in very profound ways. And I think going forward, NCSA is going to continue to be at an even higher level as sort of an engine for this. So I'll try to make connections back to this. So this talk, in fact, I didn't even have time, you might not be able to see it, but it still has illegal NSF logos behind it. So I am not part of the National Science Foundation. I have a disclaimer there because, and so I shouldn't be using NSF logos, but I just didn't have time to take them off of this talk. All right, let me get into it. So the first thing I want to point out, of course, science asks very basic questions, and that's what it's all about if you're a scientist. You want to know, for example, where did the universe come from? And then it turns out it's accelerating, and why is that happening, okay? And so you may ask initially, that's interesting, but why should we be funding that? Why is it important for science, for society, for this sort of thing? So I'm going to make these connections, and what I'm going to do is, throughout this talk, I'm going to ask some basic fundamental question about something that may seem to have nothing to do with the real world or your life, and then a couple steps away, you see it comes right back and it does something for you in the longer term. Sometimes not very much longer. So anyway, we have people here asking these kinds of questions, and I try to personalize this, so I have pictures of scientists, great scientists, and also very young scientists who may soon become great scientists that personalize this. So most of these people are either supported by the NSF, by the MPS Directorate, or they're just great scientists. For example, Roger Penrose. I don't think he has an NSF grant, but everyone knows about Roger Penrose, I'm sure. So how does consciousness emerge? And so you may wonder, what does Roger Penrose have to do with that? Well, Roger Penrose really began to think about somehow quantum uncertainty as really leading to the fundamental operations of the brain that may sort of lead to things like, free will that we may or may not actually have. Still a kind of an open question. But so there's an interesting idea that someone who's a very, very distinguished, deep-thinking mathematician and relativist could be thinking about problems like that. Another problem, how are we going to feed and power our planet? A little bit more practical, but it starts with very, very fundamental questions. For example, how can you extract energy from the sun? And it turns out we have more energy that we get through sunlight that hits the earth in an hour than if we could harness it that we could use in an entire year. So there's an enormous amount of energy there, but we don't yet know how really to efficiently take advantage of that. So this leads to fundamental questions in science. Now, these questions then begin to build connections out to the rest of what we do and the way we live. And so, for example, this question about how did the universe begin and why is it accelerating? Well, what's the nature of the matter that emerged? It turns out all of the stuff you see actually came out of a supernova explosion or out of many supernova explosions, because that's where all of the heavier elements, beyond the first couple, have been created during the supernova process. And so that comes, and then that makes not only us, but then all of the matter. So what are then the fundamental properties of the matter that emerge from the universe, and how can we use that for our advantage? And in the next, when I get into the first example, I'll take you from very basic atomic physics all the way to medical imaging, and you'll see the impact that has. How does consciousness emerge? Well, maybe a more detailed question would be, how is the brain actually structured? And so you'll find that there's a direct connection between the basic properties of atomic properties of nuclei directly to finding neural pathways within the brain. So there's some great work going on at Penn State, and I'll show you a picture of that in a few minutes. How will we feed and power our planet? So that leads to very specific kinds of questions like, how could we, for example, split water efficiently into hydrogen and oxygen, so that we can then use that for fuel, for example. So the process for doing that is not so clear. We know in principle it could be done, but how do you actually do it? So then the two basic themes that I'm going to be presenting throughout all these examples are, number one, that science innovates for society, and number two, and that's really what's really important, I think, here for NCSA. What is the impact of the compute and data revolution on the methodologies and the acceleration then of the science and these kinds of questions? And by the way, all of these questions end up requiring lots of different kinds of expertise to bring together to address them, and that's hence why we're trying to create these thematic areas at NCSA around the different complex problems that are really going to lead to innovations for society, and they're all going to depend on the computing revolution, which you are sort of the stewards of in many ways. So how does science innovate for society? Well, there's this great quote that from Rocky Kalb, and so many of you will know Rocky, a professor at the University of Chicago and at Fermilab. So he says, nobody thought in 1926 that quantum mechanics would fill the shelves of Best Buy. Okay, so, and of course, suddenly there was this revolution, but what impact does that really have on the real world, the whole quantum mechanical revolution? Well, it turns out, in fact, just looking at a GPS device, so I've got a Garmin GPS device here, and it turns out there were innovations from all 5 divisions of the Math and Physical Sciences Directorate that make that possible, and it wouldn't work without all of them actually combined into one. So for example, you wouldn't have this working if you didn't have these cesium and rubidium atomic clocks on board the GPS satellites that are so incredibly accurate, that allow the timing to be so precise. The timing measurements are critical for this thing to work. It turns out that, of course, just the display, well, that wouldn't be possible without the development of the LCD. Of course, this comes back to the light-emitting diode, which you may remember just last year there was a Nobel Prize for the development of it, and in fact, it really came out largely out of the University of Illinois. There was a lot of frustration that Nick Holoniak was not awarded the Nobel Prize, because although he developed the LED, he didn't specifically develop the blue version of that, which is what won the Nobel Prize. But that came out of the University of Illinois. And so anyway, this leads to things like displays and so on. Also, the very large scale integrated circuit designs that are needed to put all of this into a small device. So a lot of this comes out of basic material science. Now, it turns out that there are very deep mathematical algorithms without which this thing simply wouldn't work. So particularly the way the modulation and coding algorithms for the CDMA signal, and also for the military side of this, the encryption. And I'll come back into that. Some very, very basic fundamental mathematics are required for the encryption algorithms to work, or for them actually to be broken going forward into the future. I didn't realize this. Jim Ulvestad told me this, the division director for astronomy. Techniques based on radio astronomy, for example, actual quasars in the universe are used as a cosmic reference frame specifically so that the GPS systems can work. So this actually requires advances in astronomy for GPS to work. But my favorite version of this is that it turns out that these GPS systems would not work if you didn't take into account special and general relativistic corrections. So, the special relativity about how time goes slower for people moving, or general relativity, times go slower in a gravitational field, clocks go slower. So it turns out that you have to take these into account for this to work. And I've often wondered, you'd think general relativity has nothing to do with that GPS system that we all use every day, but it does. And so if you didn't have general relativity, engineers could have developed this thing and it simply wouldn't have worked, and nobody would know why. And then I wondered if that might actually have led to the development of general relativity, as an afterthought, maybe because the GPS systems didn't work. So the point is, all of these kinds of innovations have to come together for just a simple device like this to work. And then the second theme, so that I think it's a really nice example. So I'm going to just fill my talk with examples like that going forward. But the other point is that all of this now in our world these days would not be possible without this revolution, first of all due to computing, and now due to data, which is, I would say, just another side of the computing issue. So they're not like really different worlds. They're very deeply connected. So let's start the journey now through basic science. Okay, so I've got this sort of like family album of scientists from the Math and Physical Sciences Directorate. So people like Albert Einstein, one of the greatest scientists, of course, in our history. Lisa Randall, one of the deepest thinkers in modern-day physics, a professor at Harvard University now. And then Kathy Gray, that you might have seen me give another talk where I point out Kathy Gray, at age 10, managed to discover a supernova in Canada because data at a Canadian observatory were being made available for anyone to look at. And so with this open data environment, she was able to discover a supernova. And so she's now asking new kinds of questions, like where can I get data so I can do some science? Because that's the way she was brought up, right? So that's another aspect. That's what we're trying to do here by spearheading this National Data Service activity, trying to provide the ability for people to store data and then actually do things with it and discover it and then to provide data services about it. It's all to enable this sort of next generation of science. So these people have asked questions like, what are the properties of atoms and molecules? What are the properties of light? How can we improve on nature? So there are areas, for example, artificial photosynthesis. Can we actually do better than a leaf in terms of developing energy extraction out of photons coming from the sun? What's the geometry of our world? Now, this is a question you may think has little to do with the average daily life that we live, but it turns out, I'll give you an example, just 2 steps away from this, you get to the Mosaic web browser. What are the properties of numbers? Why does mathematics describe the physical world? Why? Why on earth should mathematics, that seems to come out of our heads, have anything to do with the real world and describe it so well? So I think there's a very deep mystery about that as well. So let's get started on it. So I'm going to have a series of these examples. I won't get deeply into them, but I'll just give a little bit of an example of what the basic science was and then what it led to very quickly. So there was, in the early part of this last century, I was going to say this century, but we're in a new century now, we had people like Marie Curie, Rabi, Bloch, Purcell, and later, and a little earlier actually, Maria Geppert-Mayer and so on, doing studies of basic physics and chemistry and trying to understand, for example, what properties does an atomic nucleus actually have, and what are they made of, and what about their magnetic moments, and how do they respond to a magnetic field, asking lots of questions like this. And so first of all, there's this idea that there's an atom. So the simplest atom is a hydrogen atom. It's got a proton in the middle. It's got an electron somehow in a fuzzy cloud going around it. And so this idea of an atom's been around since the Greeks. So is this just like a concept? Is it a figment of our imagination or what? Well, only in the last decade have we actually been able to image individual atoms using scanning tunneling microscopes, electron microscopes. So this is a picture of a lattice of silicon atoms, and you can see the individual atoms. And so it's true. What the Greeks were talking about, millennia ago, is actually for the first time during our last 20 years or so, been able to be proven sort of, there it is. You can see it due to new techniques that have been available. But then there were these studies people began to do. Well, there are these magnetic moments that are possible around spinning charged distributions or charged nuclei and so on. And so it turns out that just like in an analogy to a spinning top, if you have a top that's going around, it's spinning and spinning, it's got an angular momentum vector along the direction it's spinning like this, so there's an angular momentum vector coming up. If it leans over a little bit, it starts to precess. It goes around. You've seen this. So the same thing by analogy happens with spinning charge distributions because they have what's called a magnetic moment, and if they want to align with a magnetic field, and so here you got these charged particles, and they want to align with the magnetic field that they're in, and if they don't, then they start to precess around it. So people were just sort of doing studies to see, well, what is this all about, and so on, and out comes the idea that if you hit these things with radio waves, and you hit it exactly at the right frequency, suddenly there's a resonance, exactly at the right frequency. A lot of energy gets absorbed in this thing. It's called nuclear magnetic resonance, and that's what some of those Nobel Prizes were for. So again, this is like, well, basic science, and so that's cool, but okay, so what? Well, now, think about the water molecule. Your body's got a lot of this stuff in it. You're basically made out of water. And so Paul Lauterbur, who some of you may even have known, Paul was a professor here, won the Nobel Prize for medicine, because he was able to build on all of this fundamental work. And by the way, it also required a lot of mathematicians to make this practical, to think about the fast Fourier transform algorithms were important in this, computer technology to be now shrunk down and applied to this and so on, computer scientists to actually encode these algorithms on these chips, give it 20 or so years, and suddenly there's a revolution in medicine. And so everybody's heard of the magnetic resonance imaging, MRI scans. used to be called nuclear magnetic resonance, but they decided nuclear was scaring people, so they would just like leave that word off and just talk about magnetic resonance. And so it turns out, by looking at the fact that you're made out of water and your body has the water has magnetic properties, you can then go and then do a body scan and find out, without ever going into your body, what's in there. So maybe there's a tumor there, or maybe there's an abnormality that needs to be corrected. And so all of these things start happening because of that basic science. Now, other things happen kind of in parallel. So it turns out Michael Faraday, who was a great physicist. I thought of him as a physicist. If you're a chemist, you think of him as a chemist, which I only learned later. So it turns out he did a lot of things. Well, he was looking at the fact that blood seemed to have interesting magnetic properties. And so what good would that do? Well, Linus Pauling later realized that fully oxygenated blood has got different magnetic properties from less oxygenated blood. And so then some scientists realize, that's going to change the magnetic properties of the blood. And so therefore, by doing what's called functional magnetic resonance imaging, you can tell not just the structure, but also the function. You can find out what parts of your body have oxygenated blood versus less oxygenated blood, and you can begin to then really understand what's going on in your brain as it processes the oxygen and so on. So these are basic things that people came up with, but it all had to be integrated in order to really be able to do this kind of payback, let's say, to society. So, by the way, I'll point out another thing. These things require very, very powerful magnets. And so, in fact, they require superconducting magnets. Superconductivity, by the way, and they're so powerful, by the way, this is a pallet that's wasn't properly nailed down, latched down. They turned the thing on and the whole thing went flying off like that. So we're talking about very, very powerful magnetic fields that are possible through superconductivity. And in fact, I show a picture here of John Bardeen. So hopefully you all know John Bardeen was a professor here, and one of his 2 Nobel Prizes was for the theory of superconductivity. The other one, by the way, was for the invention of the transistor. So talk about something that's really impacted our lives. So this is very fundamental science. In fact, the only person to have won 2 Nobel Prizes in the same field, that's John Bardeen, who helped really build this physics department into a world-class department. So another example about how all of these things have to come together, and a lot of it happens on this campus. Okay, so where could this go in the future? So there was some really exciting work done a few years ago by these 2 scientists at Penn State and Northwestern on imaging the brain. And so this is on the cover of Physics Today in 2012, just a few years ago. Well, they're actually able to map out in the brain neural pathways, bundles of nerves in the brain in great detail, building on these basic techniques. And so the main thing is, you tend to think of your brain as sort of like full of spaghetti, right? And then it's a jumble of thoughts, and you can't get anything out of it. And especially these days, the email we get and so on. Well, this has a very regular structure. These neural pathways are actually in a 3-dimensional structure. They're at right angles to each other. So there's a very interesting regular structure in the brain that keeps information flow going. And so this is sort of a revolution in our understanding of the brain that's coming back to basic science activities. Okay, well, bodies have more than water in them. And so almost all of magnetic resonance imaging is based on the fact that there's water in your body. And so, but you've got a lot of other things in it. So what if you started looking at different kinds of compounds, different chemicals, different nuclei and so on, ions that are in your body. And so, for example, a new version of this is now using sodium-23 atoms, and they can be used you need very powerful magnetic fields. So there's a thing called the National High Magnetic Field Lab at Florida State, where they have extremely high magnetic fields, a 21 Tesla magnet, which is about 1 million times the magnetic field of the Earth. By the way, this was funded by the ARRA funding, the stimulus package from Obama around 2008 that led to the development of this magnet. So this magnet is then being used to say, could we use other compounds in your body to image things? And so, for example, mouse tumors have been imaged using this as a marker. So imagine in another couple of decades, complete chemical body scans that would just tell you everything that's going on inside your body. So that's where this technology could be leading us. Another example, where this is coming to. So you've all heard about quantum computing at some level. Well, at the simplest level, you have an electron that has a spin 1/2. And so according to basic quantum mechanics, it's either like spin up or it's spin down. So that sounds like a bit to a computer scientist. So the question is, could you actually build a computer using spin as the major thing that's telling you the information, the basic information of a bit? It's either on or off, or it's plus 1/2 or minus 1/2, and so on. And it turns out people are now learning how to actually manipulate at the very subatomic level. And I mean subatomic, at the level of electrons and so on. There's a whole field of science called spintronics now, trying to develop the computing devices out of what would be called quantum materials. Or another version, not exactly of this, but a similar sort of direction coming from basic science, is magnetic graphene. So graphene, for which a Nobel Prize was awarded, I can't remember, 2010, it's the strongest material that we know of, and it's a single layer of carbon atoms in this particular lattice is strong enough. So I read one of these sort of popular science things, if you made like a hammock out of graphene, a single layer of atoms, you could put a car on it and it would be able to hold it up no problem. We're talking about a single layer of atoms, so it's extraordinarily strong. And then, so people have learned how to magnetize this, and you put these two together, maybe you can use this for new kinds of semiconductor or computing devices. And particularly, this seems to be a promising area to develop three-dimensional microprocessor chips and memory chips using graphene as the fundamental substrate for this, because now it can be magnetized, and then you can think about the quantum properties of this. So this could be leading to a revolution in supercomputing. Not just supercomputing, but all kinds of computing. And in fact, everyone, I think, thinks that there's promise and sort of on a 10-year timescale for this. Okay, I'm going to get away from spins and nuclear things, and I'm going to move into a little bit more into chemistry. And so everyone, probably at least at some point in their lives, had to learn something about the periodic table of the elements. So I'm not going to talk about that part. I'm going to look at it from a different point of view. How do these elements, how are they categorized? In the sense, are they benign? So they basically don't really do much. Are they expensive? They cost a lot of money if you needed some. Are they radioactive? Are they toxic? What about, are they scarce? And so this is a really important one. Some of them are scarce. They're scarce now because we're simply running out of them. But some of them might be scarce pretty soon because we either run out, there's a natural disaster, or there's some political manipulation. Some country has most of it and they decide we're not letting others have it because it's very valuable and the price goes up. And so this sort of thing is happening. And so there are lots of reasons why finding new materials that are cheaper and easier to deal with and maybe more abundant could be substitutes for the basic elements. This leads us back to material science. And so let me give you an example where this hits home. How many of you have a car like a Prius? I know Donna has one. So a Prius is a very complicated vehicle. A car used to be made out of 5 materials: wood, glass, steel, rubber, and brass. That was it. That was all that was in a car. So pretty easy to get the stuff to make one. But for something like a Prius, which is an example of what's in most modern cars these days, there are lots of things that were on that chart that were not easily available. For example, these 3 that are needed in your car are scarce, and they could become more scarce. So a lot of material science effort is in actually building substitute materials for these things that would be either cheaper or easier to get in case of a political crisis or a natural disaster or something like that. So this brings it right back to what we drive every day. Okay, I'm going to switch gears again. Somebody might ask a question, what is light made of? And why does that matter? So there's this big debate between 2 contemporaries who really were at each other's throats about this. Newton says it's a particle, and Huygens says no, it's a wave. And unfortunately for Huygens, Newton won this argument for a couple centuries. Turns out it's more complicated than that. So you may know, if you studied any quantum mechanics, there's the wave-particle duality of matter, and there's this strange thing. But so there was this big argument. But the fundamental observations about light and what its properties were leads to amazing innovations in our lives. So let me give you a couple of examples. So This just blew me away when I learned about this and when I saw this. So I've had the privilege as the MPS assistant director to travel to some of these sites, and I've seen, for example, the Gemini telescope. There are two telescopes, one in the southern hemisphere in Chile. And so it has a laser beam that's being shot into the sky. It's not just receiving light, it's actually sending light up. And why is that? Well, the background is that most of what we know about the universe comes from light. We look up in the sky, we see stars, and if we're really good, we might see galaxies, or we need telescopes to see galaxies. We may see other things and so on. Most of it comes from light, but we're living on the planet Earth, and it has this atmosphere. Sometimes it's cloudy and you can't see it at all. Sometimes it's as clear as it can be, and you even go to the top of mountaintops, but there's still a lot of atmosphere there, and it's very turbulent. So the atmosphere, especially 80 kilometers up, is just going like this because it's buffeted by all kinds of forces up there in the upper atmosphere and so on. So it is messing up our view of the universe. So some astronomers, going way back into the middle part of the last century and then sort of using technologies afterwards, said, you know what, if we could find a way to correct for that. So the photons are coming down from some distant galaxy, they get into the upper atmosphere, then they start getting knocked around. So how could we correct for that? So they said, here's an idea, and this would be what a physicist would come up with, like an idea in principle that probably is impractical, could never work. So let's shine a laser beam up into the sky, and let's shine it exactly in the direction that we're looking, and let's tune it to the sodium atoms that are up in the sky, say 80 to 100 kilometers up in the air, and above the ground. And so they will absorb that laser beam light because it's tuned exactly to the right resonant line, and then they will re-radiate it back down. And then you can tell, because of the Doppler shift, they're moving around, you can tell which way they're moving. And if you know that, in principle, you could correct for it by saying, deforming the mirror that the light is coming down into. So you deform the mirror. Now, this just sounds absolutely crazy. This could never work. But turns out that it does. And so there was a center, NSF funded, for a Center for Adaptive Optics that worked out a lot of the technologies for this. And it is unbelievable in that you can actually correct for all of this turbulence in the sky. And in fact, in certain wave bands, you can do better than the Hubble Space Telescope by this adaptive optics technique. So actually, the light comes back, you measure it, you understand which way the molecules are moving, you use that to correct, and then you deform the mirror at the level of hundreds of times a second, potentially. That's about sort of the maximum of where we are right now, and you can then correct the image. And let me show you how amazing this is. So this is a picture. This is an image of a star. And look, it's a lot of turbulence. This is what's called terrible seeing. And so the seeing for an astronomer is very bad. It's like sort of there's a star there, and here's what it looks like if you project it down. And I'll show you in real time what happens. And then I turn on the adaptive techniques for adaptive optics and show how this gets cleaned up. Oh, there we go. Look at this. So it's terrible. How could you do any science on that? Turn on the adaptive optics, and it does that. It's actually cleaning that image up in real time. And so it's amazing how that could work. Now, so that's great for astronomy. And in fact, it's immediately applied to things like looking for planets. So how many planets do we have? Who's going to give me an answer? How many planets are there? 1,800. So when I was in school, I learned there were 9. Okay, so then maybe there are 10. Oh, wait a minute, Pluto's not really a planet. But it turns out, so the day before I gave this talk, XKCD came out with this great image, which is now way out of date now, but it says there are 786 known planets. In fact, that was 3 years ago. So now there are about around 2,000, I think, known planets these days. And so it's astounding. And these planets are really very, very far away. So the techniques are enhanced tremendously by this adaptive optics technique that I was talking about before. So that's one of the ways that we use to actually, or that astronomers use in order to really find exoplanets. And here is the first actual exosolar system that has been imaged. So it's a solar system. And there could be somebody there applying that same technique, back at us right now. And so actually, People are now beginning to look at, okay, not only are there planets there, but what are their properties? What are their chemical properties? Is there any sign of industrialization if there's potential for life there, you know? So what is that going to tell us? And we're going to have some pretty interesting observations in the next few years that are going to begin to answer some of those questions. So, but this basic adaptive optics technique then gets applied directly back into medical imaging. So for example, this is a picture of a retina. And here's some retina, 2 images of retina, one with the best techniques available without adaptive optics, and then with adaptive optics. And you see the improvement in the image. And so this starts with a crazy idea among some physicists, gets applied by astronomers, and then it gets turned into actual medical technologies that's beginning to revolutionize the way people do medical imaging already. So there are a few examples of this. I think I'll just skip on because I'm running a little bit late here. Okay, so this is Emily Carter, who's a chemist at Princeton. Who knows who this is? He's a chemist. His name is Frank Capra. So Frank Capra, a great movie producer, was actually a student at Caltech and got a degree in chemistry. And then so it turns out he used to put things about chemistry in his movies. And so here's an example, which I got from Luis Echegoyen, who was the division director for chemistry at NSF the first while I was there. So, see, oh, I forgot, I need a microphone on this. Can I, maybe this will do. It's probably good enough. Let's try this.
We wanted to find out what made the grass grow green. The biggest research problem in the world today, and I'll tell you why. Because there's a tiny little engine in the green of this grass and in the green of the trees that has the mysterious gift of being able to take energy from the rays of the sun and store it up. Well, we thought if we could find the secret of all those millions of little engines in this green stuff, we can make big ones. And then we could take all the power we could ever need right from the sun's rays, you see? We worked on it and worked. At night we got so excited we forgot to sleep. If we make just one little discovery, well, then we left school. Now he's selling automobiles. I'm in some strange thing called banking.
Okay, so he ends up going into banking instead of changing the world. But the idea is the passion was there. But in a few minutes, I'm going to give you an example about how banking has actually turned around to develop some very, very fundamental mathematics that has also revolutionized the way we describe the world in terms of mathematics. So this idea about sunlight, I mentioned this, more sunlight strikes the earth in an hour than we could use an entire year, but we just don't know how to take advantage of that yet, right? So there are a lot of projects around the world that I was highlighting in particular. There's a Center for Artificial Photosynthesis at Caltech that manages to integrate these different kinds of activities, from photonics to polymers and building, sort of, for example, flexible membranes that are actually electronic circuits. And, you know, as you probably have all seen, we're like one of the world's leaders in developing that, the whole MRL. John Rogers, if you ever have a chance to talk with John Rogers, who's the head of the MRL, he'll show you on his fingernail the kind of circuitry he's built in. And then tattoos he's got built into his arm that have near-field communication built into them and so on. So you can like hold your iPhone up to his arm and it will broadcast a message. So building these sort of technologies into sort of biological systems is a part of this. And then it also brings in, of course, nanomaterials and so on. So the point is, this is highly integrative science to begin to look at a very complex problem. And as I'll argue in a few minutes, it also depends tremendously on the computing capacity that we're going to have. And we're going to have all of this right here in-house at NCSA, where I think we can all begin to participate in some of these things, and I think they'll be very exciting. So let me ask another question. What is the geometry of our world? So most of us grew up at least learning something, maybe hating it. I loved it, but basic geometry. You know, how many degrees are in a triangle? Well, 180, and so on. And so Euclid worked a lot of that stuff out. There was one of his so-called postulates, though, that was really troubling to mathematicians for centuries, which was parallel lines never meet. And so people really began to kind of question that one. Is there's something wrong with that one? And people like Riemann, in particular, who was a great mathematician from the 19th century, began to look at this, and Emmy Noether and others. And then Albert Einstein comes along and integrates all of this by asking new questions. And I'll show you in a second how that has impacted our daily lives. So the first thing is this idea about basic geometry. So we would it seems logical that two parallel lines would never meet, but look, they look like they're getting closer at least. And then this triangle's got 180 degrees. Well, maybe it doesn't. Maybe if this were like a curved space, if it were a curved surface, not just a flat surface. So Euclid did everything assuming so-called flat geometry. But, so something might happen. So we're actually in a curved surface, and look, those lines are getting closer or further away from each other. And so thinking about this more mathematically, if you have what's called a positively curved surface or a sphere, and you draw a triangle on it, it's got more than 180 degrees within that triangle. And if you have it on what's called a negatively curved surface, and it's the thing called the Gaussian curvature that tells you about that, it's got less than 180 degrees inside that triangle. So the point is, geometry depends on the actual space you're in. Now, you might say, well, okay, that's very artificial. That has nothing to do with the real world. But then Einstein came along and just like threw everything out and said, I think this is really different. He says, I think objects move like this. So who's going to catch this? Xiaowen or Donna? Watch out. Why did that Satsuma take that path? Why did it do that curve? And so Newton would have said, well, it's just moving in a gravitational field. You threw it up, but gravity pulled it down. Einstein says, no. It's the straightest possible path in a curved space. So he says, I think somehow gravity is curving the space, and then things move along in paths that are just as straight as they can be, but the curve underlying geometry of that space is curved. So Einstein asked that question, and that was his answer, and he developed an entire theory out of that sort of very elegant idea. And that's one of the beauties of Einstein's work everywhere. It's always the simplest, amazing idea taken to its logical and mathematical extreme. And he had this great saying. He says, a theory should be as simple as possible, but no simpler. Okay, so that's Occam's razor, I guess. So here are the equations that he wrote down. They look very nice when you write them in this sort of form, but this is actually 16, or how many equations is it? Let's see. I was looking on the internet, and I found this kid talking about them. There are essentially 10 equations. They're extremely complicated. No one can spot a solution to such a system of equations. They're just too complicated. So the only hope that we know of now, at least, is to use numerical means, to try to use a supercomputer to get numerical solutions to those equations. So that was somebody I know from NCSA during a different era, at least of hair color. So the point is, the only way to solve those equations is really by large-scale numerical methods. And Larry Smarr was the first person to really try to do that. And he went through a lot of difficulty trying to convince people that what he was doing is really science and not just sort of like garbage in, garbage out on a computer. And so there was this going on for a long time. Now it turns out it's almost routine. Any graduate student or undergraduate working in relativistic astrophysics now has tools at their disposal to solve Einstein's equations. The most complicated equations in all of mathematical physics can be solved routinely because of advances in computational science. And that really is what the heart of NCSA is. So this is just an example where this is now routine, and now we can solve these equations, but we need to apply them to real astrophysical events like black holes colliding or neutron stars colliding and so on. And so general relativity has moved from a single investigator working in isolation to very large computational and data-enabled science and engineering teams. And that's, again, this idea of building these thematic areas at NCSA so we can become the home of some of these teams to help us address these complex problems. So what impact does this have on innovation? Well, here's a great picture. That's Larry Smarr. Some of you may not even recognize Larry in that era either. So Larry was working with some of the great scientists of the time. That's John Wheeler. So John Wheeler is the guy who invented the term black hole. John Wheeler was, among other things, Richard Feynman's advisor, to give you an idea of the amazing breadth of fundamental physics that John Wheeler is responsible for. So anyway, Larry was trying to solve these problems of two black holes colliding, couldn't do it, needed bigger and bigger supercomputers, wrote an unsolicited proposal to the NSF. It's what led to NCSA and the other supercomputing centers that are still supported by NSF. And it also had a lot of practical implications, and here's one that I'll show you, which is, of course, I'm sorry, when I did this, I didn't have a picture of blue waters years ago, so I think that's the Kraken machine, which is no longer operating, is it? Anyway, so ours is bigger and better. And it led directly to this. And I have told this story at NSF and to many people, and many of them don't really quite believe it. They're like, oh, that would have happened anyway. I don't believe it would have happened in the same way. So Larry was very, very focused on how you can extract information from complex systems like simulations, and visualization was a really, really important part of that. And that sort of pervaded the culture here. And so people began to think, how could you use it, for example, to visualize information on the internet? And that's what led ultimately to the graphical web browser. And so 2 years ago, Larry was given the so-called Golden Goose Award from the AAAS, in part for really driving the development of NCSA and then its other centers as well, but then all the things that came out of them, including things like the Mosaic web browser. So I was just pointing this out in my talk. See this, even in Internet Explorer, there's this little thing that says, it came out of NCSA. But studies have shown that this has added over $1 trillion to the world economy. And I want to point out, this is something that was really a message to some of my physics colleagues. You know, you don't want to force your fundamental scientists to do things that are so practical, you know. But Einstein himself has an early patent on refrigeration that he got. And it's quite interesting. He was working in Berlin at the time, and he filed a U.S. patent for refrigeration that actually is still valid, people still are actually trying to build a refrigerator based on his basic physical design for it. All right, so let me move on. I'm running a little bit long here, but I want to get to a couple more things. So I want to talk a little bit about fundamental mathematics. So some great mathematicians, you might have read recently in the New York Times, there was an expose on Terry Tao, who's considered these days sort of the Mozart of mathematics, just seeing far deeper than most other mathematicians. And so there are a number of people like this. Eugene Wigner is a physicist, but so a lot of mathematics. And so one of the questions is, what does mathematics actually have to do with the real world? And so here's an example. There's a thing, if you're a mathematician, you'll know this. If you aren't, you probably won't. But it's a fairly simple formula that you could know from sort of high school algebra. There's just this thing called the Riemann zeta function, and where there's this variable s that goes into it. So it's a complex number. So this you could write down. This is basically high school algebra. But Riemann had this thing, and he wanted to find out what are the zeros of this solution of this function. That is, for what values of s will this function actually be equal to 0? And he could not prove it. But he had a conjecture that said all the solutions to this equation have got to have a equal to 1/2. And so this seemed like a very simple problem in mathematics, but it turns out it has not yet been solved after centuries of the greatest mathematicians working on it. But if you assume this true, if you assume the Riemann conjecture is true, then it tells you a lot about the distribution of prime numbers in number theory. And so, okay, big deal again. But let me show you what it means. So prime numbers are like the building blocks of all bigger numbers, right? So if you say, how do you factor this number? You have to find what prime numbers, when multiplied together, give you that number. So who can do that? Jennifer. 2 times 3 is 6. 2 times 3. So that's easy. So what about this prime number? What are the factors? Is that a prime number or not? 93 digits. Well, 193 digits. So this is the kind of thing it takes a supercomputer, or at least many, many months of time on small, we would consider that a fairly small supercomputer, but most people wouldn't. It takes months to factor this to figure out if that's a prime number or not. And so this is one of the bases of cybersecurity. So assuming that there are these large numbers that in practical time cannot be factored, and then you use that to build out your basis of things like cybersecurity. So at NSF, there are all these little RSA keys. We don't use them here, but they're based on this principle of factoring large numbers, which really comes back to Riemann's work on the Riemann function and the zeros of it. And so, but there are new things that are going on. People are looking at quantum information science again, and if you assume you have a quantum computer, there are ways you can factor number extremely well, and so on. And there are people looking at now the kinds of algorithms that you would have if you wanted to have very secure, provably secure encryption that would resist even quantum computing attacks. So this is going to be a huge area of research, and I think we are really well situated with the cybersecurity group here to continue to be one of the leading activities. And NSF, the Congress is looking at every year to put more money into NSF about cybersecurity. So it's clearly a growing area because it comes right to the heart of national security. Okay, so let me just do one more example, and then I'll try to wrap it up. But I love this one so much, I want to give this one. So the question is, why does mathematics apply to the natural sciences? I wonder about this a lot. It's one of those things. How can it possibly have anything to do with it? So for example, so there's this guy, Wigner, who you could look this up, the unreasonable effectiveness of mathematics in the natural sciences. He wrote an article around 1962 or 3, something like that, where he was one of the great scientists, a great physicist of the last century. And he sort of said, why could this possibly be? And so some of the examples that I'm going to just mention here were in that paper. So I just urge you to take a look at that. It's very readable by anybody here. So for example, it starts off by talking about the statistics of population. So people studying populations and sort of distributions of people and so on, it turns out the number pi comes up in their studies all the time. And pi is the circumference divided by the diameter of a circle. So all circles have that same value pi, unless, by the way, if they're in a curved space, then they don't. But in flat space, they do. So how could that possibly have anything to do with the populations of people? That's just how could that be? How could that be? So the next example is imaginary numbers. So this drove people, mathematicians like Euclid, crazy. Literally, there's a story that it drove him crazy. The square root of a negative number. So that's just nonsense. And over the years, that was ridiculed until fairly recently, in the last few hundred years, that whole idea was ridiculed. But some people took it more seriously and said, okay, well, let's just assume that we call this number I the square root of -1, because you can't possibly have two numbers multiplied by each other that give you -1, right? So anyway, that's that. And so let's assume that exists. And then, this is the really amazing one. So Bernoulli was a great mathematician, but he was also very practically oriented. So Bernoulli wanted to know, if he put money in a bank and he had interest, how much money would he have at the end of the year? So he wanted to know, what happens if I have like a 5% interest rate? I want it not just to be like 5% for the whole year. I want it to be compounded, like every 6 months apply that, or maybe every day, or what's the limit as you just sort of continuously compound interest rates? And the number E pops right out of that. So this is a transcendental number that was discovered by Bernoulli, and it came from his looking at practical problems of banking, back to Jimmy Stewart's thing. He thought he was wasting his life by going into banking, not doing photosynthesis, and it turns out that banking actually led to the number E. So what's so special about that? Well, these numbers that couldn't possibly have anything to do with reality or even with each other, you can prove this equation, which is like E, that's the number you get from banking, to the power of I, that's the number that can't possibly exist, pi, which is the ratio of a circumference of a circle to its diameter, to its radius, is related to the other fundamental numbers 1 and 0 by this equation. So the 5 fundamental numbers in all of mathematics are related by this simple equation, and they came about by very different sorts of studies. But this basic equation and sort of the generalization of it, with the sort of expansions and cosines and sines and so on, is the fundamental mathematics of basically all of engineering. And so without this, we wouldn't be able to build buildings like this. And so it's astounding. All right. And so, Wigner just says, well, this is a miracle, and the appropriateness of mathematics for the laws of nature, why on earth does this work? I think no one knows, even now. So where is this going? Well, I'll just point out that there are lots of questions in math that would seem to have nothing to do with the real world necessarily, but they do. And it turns out this one was solved just a few years ago. This looks very simple. This is Fermat's last theorem, which was never proved. Surely was never actually proved by Fermat, but it turns out it was proved a couple years ago. Okay, so just want to conclude then by saying all of this fits into where is the scientific method taking us and how is it changing? And I want to sort of just mention again, we sort of moved the sort of fourth paradigm, moving from Galileo, father of data-driven science, saying you had to take down data in notebooks, you had to then reproduce your work and so on. That's a fundamental aspect of science. And then moving to sort of new scientific heroes like Kathy Gray, living in an open world of open science and then discovering things like supernovae. And so I've given these slides before, so I won't, I've run out of time. But I'll just point out a couple of things about them that going back to sort of the problem that I talked about earlier with Larry Smarrs and what I spent a lot of my career on, moving from very early theoretical work about what happens when two black holes collide by Stephen Hawking, and then moving to the present day, the main trends I want to talk about are larger collaboration, so one person, 10 people for this calculation that was actually carried out here at NCSA by the group here that I led years ago, that Joanne was a part of. Now the three-dimensional version of this actually made the cover of Stephen Hawking's 60th birthday book, which I'm very, very proud of. Years ago, when my work is all forgotten, his work will be remembered, and that image is on the cover of his book at least, so that's very good. So the point is that many collaborations to solve these complex problems are getting larger, and they're using more and more complex cyber infrastructure, and so we are the home of that. So I'll just stop in a second here, scale to the very end. More and more complex versions of this. Luciano Rozzola doing neutron star simulations, gamma ray bursts, the whole thing we talk about here now with providing, hopefully getting involved with data sources for LIGO and data management. We're already doing the Large Synoptic Survey Telescope, the Dark Energy Survey. We're leading a lot of the work in simulations of sources of gravitational waves, and it's going to be a very exciting time going forward. All of this data has to be moved around on optical networks because there's so much of it. This is our laboratory of an astrophysicist in the next few years. It's going to have all of these instruments around the world generating petabytes of data, potentially LIGO being partly built in India as well. That's probably going to happen. And then simulations that bring it all together. So I have a picture of the Blue Waters petascale computing facility there. This is the environment that we are prototyping and then building and then providing and then using ourselves as we develop these thematic areas to revolutionize this. And this will pay back into society in big ways. So I will say, you see this in all areas of science. And this is the very last thing I want to say about this. This leads to people asking, of course, new questions. And so I have sort of a number of people from across math and physical sciences, people that have been supported by MPS over the years. Gerhard Sieder doing materials, Larry Gladney, cosmology, Christian Ott doing basic astrophysics, Seth Lloyd doing quantum computing, Jack Shostak looking at how life forms, even building artificial DNA. Designing your own DNA, putting it in a cell, or figuring out how could the first cell have actually formed. So this kind of stuff, what Klaus Schulten is doing, being able to model from first principles how life might emerge out of chemistry. That's kind of at the level that we're at right now. So the next couple generations, questions like that we're going to be able to answer. And then so Kathy Gray will be asking them in a new way on data. And I have my answer to this. Where's the journey taking us? I just couldn't help quoting Star Trek from J.M. Barrie, second star to the right and straight on till morning. So I'll stop. Thanks.
Questions for Ed?
Are the slides available online?
I can make them available. We'll make them available.
About 2,000 ask Larry Smarr what makes mathematics work. I have him on videotape
And what
giving
did
an
he say?
answer. Next week when he gives his talk, I'm going to ask him if we can make that publicly available.
Okay, oh, great, okay.
But part of it was, you know, the Smarr-esque, you have to have faith kind of statement. But this has been an argument that has gone on since Plato and his student Aristotle. Why has mathematics worked? And there are two models. And one is that the reality out there is mathematical, and you're discovering these perfect phenomenon, and that the mathematics describes the perfect phenomenon with Bertrand Russell and people like that that would be on that side, Plato's side. But Aristotle pretty much said mathematics is an invention of the mind, of the human mind, to basically encode patterns. I'd like to know what side you are on. Are you Aristotelian or Platonic?
I'm an integrator, so I take the best of both. But you know, there's this crazy idea that maybe isn't so crazy, that we're actually living inside a big simulation. And so some people are saying the reason why pi and these numbers, these sort of perfect numbers, come up in the real world is that we're just part of a computer model, and it's a very sophisticated one. And it's so sophisticated that it seems very real to us, but that's all we are. We are agents in a big agent-based simulation of some kind. So I mean, serious scientists actually are talking about this as if I don't know, it seems crazy, but who knows?
I'll be very quick, and I'll preface this by saying I'm a sociologist, so we ruin everything. But I guess it's more of a comment. There's a lot of potential, and there's a lot about the possibilities of what we can do. And I hope that as we're doing that, we're also asking the question of whether we should be doing these things.
Absolutely, right. It's scaring a lot of people what we're doing these days in science. I mean, so if you have people like, in my field, you know, people like Stephen Hawking and Frank Wilczek, who's a great scientist, has a Nobel Prize, are very concerned about artificial intelligence and where's that going. And same people like Martin Rees, who's one of the great, he was the astronomer royal, you know, in Pirates of Penzance, but there's actually a real person. And so Martin Rees believes that biological development of biotechnologies and so on will actually lead to a terrible accident for the world. And so we have to be very careful. I mean, there are a lot of examples like this, of course.
I was with you 20 years ago. I just wonder if you have thoughts about 20 years from now. Your iPhone in 20 years will have the power of blue waters. And you're going to have something absolutely amazing.
It won't take that long.
It won't take that long for you. Your old iPhone. I use an old iPhone. I don't have the 6. What are your predictions for 20 years from now about supercomputing and maybe about this center? What would you envision in 20 years? I know it's a difficult question.
No, I think it really hits home when you say, what about this center? And so I think, first of all, the fact that no one can answer that question correctly means that we better be very nimble about going forward, and we better keep our eyes open, and we better be pushing the edge. And so that's been part of my mantra about innovating. We've got to be part of the innovating part of this equation and not just responding, because you can't lead by responding. You've got to be leading by innovating. And so I'm pushing that very hard. So I would just say that's why I want to make sure that we are in the best possible position to continue to lead, as no matter what happens in that 20-year time period, but it's going to look really different.
Let's give Ed one more